All right, last week we did a purely on paper experiment. This week is going to be our first real laboratory experiment. We're going to look at the absorption spectra of 3 different conjugated dyes, and then we're going to interpret them with a simple quantum mechanical model. As with all the experiments this semester, the experiment's fairly easy, the interpretation is much more difficult, much more theory heavy. So here's the experiment. We're going to look at 3 different conjugated dyes, 3 different cyanine dyes, this one, and this one. And the difference between them, these dyes absorb strongly in the visible, and the reason they absorb strongly in the visible is because they have these large conjugated systems, and the size of the conjugated systems varies between the 3. And that will give us, we're going to use a simple model that works, can be made to work pretty well for any one dye. But the question is, when we change the size of the conjugated region, change the dye, how well does the model continue to work? If it still works even for all 3 of these dyes reasonably well, then it's not a bad model. If it only works for one dye, then maybe not so good. So, first of all, the difference between these dyes can be understood in the number of bonds that are involved. So 1, 2, 3, 4, 5, 6, 7, 8 conjugated bonds in dye number 1, 10 conjugated bonds in dye number 2, 12 in dye number 3. And those conjugated bonds, of course, have a pi conjugated system above those bonds. And that conjugated system has a certain number of electrons, 10 electrons for the first case, 12 electrons for the second, and 14 electrons for the third. That number of electrons includes this lone pair on the nitrogen here, so they aren't all electrons that are on the carbon atoms, but the pi system is thought, or is modeled at least, as including that lone pair on the nitrogen. So that's the number of electrons. What's going on with these molecules? Well, we can build a very complicated model. We can start doing some real quantum mechanics. We can start getting out Gaussian, whatever it is now, 2016 or 2018 probably, maybe even 2020 now, and and do some calculations, and that'll give us energy levels and stuff. But let's look qualitatively at what the bonding should be like, just on a sort of freshman level before we start hauling out the computer. We're never going to get the computer out for this lab. In fact, we're going to use this simple model. Here's the pi or SP core network of bondings. We have sp2 hybrid orbitals on the carbons. We've got 1s orbitals on the hydrogens. Those overlap, and at every overlap in a sort of valence bond picture, we imagine that there's a single bond there, and a single bond here on the hydrogens as well. And that makes a sort of single bonding sigma 1s kind of network or sigma bonding framework. Our spectroscopy is not even going to touch that stuff. That sigma bonding framework is at much deeper and larger energies than we're going to be investigating in this experiment. And so it's going to remain untouched, but it is there. The spectroscopy that would show us something about this network would probably be in the fairly far UV. Instead, we're going to look at the pi or p orbital network that's on top of the sigma bonding network. And as everybody I think here knows, when you have a bunch of p orbitals that are all parallel and all repeating over a whole pi network like this, then they form a set of molecular orbitals. And those molecular orbitals look something like this. I mean, this is not the result of a calculation. This is from just general experience. So they don't look exactly like what I've drawn here, but they look more or less like this. If you were to actually get out one of the quantum computational programs and set this molecule up and do the calculation, you'd get something that looked roughly like these things. First of all, there's going to be one molecular orbital at the lowest energy that has all the same sign throughout the whole pi conjugated network. Then there'll be a second molecular orbital as a slightly higher energy that's got one node. So there's a plus region over here, but then a minus region across that node. And then a third one that's got two nodes, and therefore an alternating sign, plus, minus, plus. And there will be higher molecular orbitals as you go up with 3 nodes, 4 nodes, and so on, depending on how many electrons you have. Some of these orbitals will be occupied, some not occupied, depending on how high you go. But they'll all kind of look like this. They'll basically be alternating in sign. And you can map or make a correspondence in your mind, at least, between the shapes of these actual MOs, molecular orbitals, and the particle in a box model, where you think of the electron as just running inside of a box. There's the ends of the box there over this whole network of p orbitals of carbon atoms. And if you look at the particle in a box model, you get a pattern that looks very much like, qualitatively at least, like this pattern of shapes for the molecular orbitals themselves. You get one, the lowest mode is all one sign, all positive. The next one starts out positive and then changes sign, has one node. The next one has 2 nodes. Oops. Yeah. 2 nodes and so on. And the reason why there's this correspondence or similarity between the particle in a box modes, the very simplest of all simple quantum mechanical models, and the actual quite complicated molecular orbitals you'd get out of a calculation, is that essentially the same kinds of things are happening in both cases. The electrons really are in a box. The electrons really are running over a region without very much. I mean, the question is, as the electrons move over the carbon atoms here, is the potential energy the electron sees really flat like this? Well, the answer is no. It really has some variation, but it's not a big variation, I don't think, because those pi electrons are moving around in the presence of these sigma electrons, and the sigma electrons are sort of shielding most of there's core electrons below that. So the nuclei of the atoms are mostly screened and shielded by those other electrons. And the pi electrons are mostly moving in an essentially flat potential inside of a box. They can't get out of the limits of this box. And so you get behavior that's at least qualitatively like you'd expect from a PIB. What we're going to do in this experiment is take data with the spectrometer, and then we're going to fit some of that data, 2 types of that data, to this PIB model and see just how good we get from it. All right. So here's the experiment. We're just going to take 3 different spectra for the 3 different dyes. These 3 dyes up here, in fact. And of course, we choose these 3 dyes because they have different conjugation lengths and therefore allow us, as the size of this box changes, if it's small, you get a different set of energy levels than if it's large. And so as we're changing the size of those molecules, we're changing the size of the box, we're changing the energy levels. And the question is, does that model track across all 3 molecules? So we're going to take 3 different spectra, and what we're going to find out is if we look at psi here, which has the shortest, the smallest conjugated system, then we get an absorption peak somewhere in the neighborhood of 600 nanometers. If we go to carboxy, the next biggest one, the peak has moved to the red out to 700 nanometers to lower energy because there's a bigger box. And if we do the dicarboxy case, then it's moved out to 800 nanometers, again because there's a bigger box. So qualitatively, things are going in the right direction. You expect as the box gets bigger, the gaps between the states for a simple PIB model start getting smaller and smaller. That would cause absorption peaks to occur at longer and longer wavelengths, and that's in fact what we see. So qualitatively, the model is okay, and we're going to do a quantitative comparison here. All right, so we're going to do 2 things. First, we're going to measure the peak positions, and I've said those already, and then we're going to fit those to the PIB model. As I say here, that works pretty well. I'll say something more about that towards the end. The other thing we're going to do is to calculate Well, on paper, we're going to calculate transition dipoles and something called the Einstein B coefficient, which is a measure of the strength of the absorption band. So it's basically it's very closely related to the area under the curves of these peaks. The higher the peak is, the stronger the absorption band. The wider the peak is, the bigger the area under the peak is, the stronger the absorption band. And we're going to find out, and we can do that, we can calculate that same quantity from the particle in a box model, and we can compare the values we get from both and see if we get a good match or not. I say it's really bad here, and it is really bad, which is showing that the particle in a box model is good for some things, not good for other things. All right, so what gives rise to a peak position? Well, the basic thing is that if you've got an initial state, a ground state for the molecule, and then a first excited state for the molecule, there's an energy gap between the two, and that energy gap has to match the energy gap for the photon coming in. That determines the wavelength or the frequency of the incoming photon, and therefore the position of the absorption peak. The actual states of the molecule aren't the molecular orbitals. So if these are the levels, the energy levels of the molecular orbitals, some of those molecular orbitals are filled, right? If we had 6 electrons, these first 3 would be. We've actually got more than that, right? 10, 12, or 14 electrons, depending on which molecule. And so some of the molecular orbitals are going to be filled. And then the transition is from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. So your initial state, the initial state is the ground state here with everything in the lowest possible orbitals. And the final state is this one here, where one of the electrons has been promoted up to the next highest molecular orbital. So here's the actual particle in a box model. Here's the energy levels for the particle in a box. So there's all these constants out in front. They give a value that we'll have to calculate. Especially, we don't know the value of this L, right? How big is the box for our molecules? That's that length, that L is the length of the box. Well, our molecules don't really have a box. They have a certain number of chemical bonds, and we can relate that to the box, and we'll see how to do that. And then there's a quantum number n, and then the energy levels depend on the quantum number n as n squared, which means that the energy levels, well, there's no n equals 0 value. N starts at 1. So there's an n equals 1 value, which will assign an energy E0, which would just be this bunch of constants here. That's E0. And then the next one, n equals 2, will be 4 times bigger than that, right? Because you're going to put a 2 in there and then square it. And the next one will be 9 times bigger, the next one 16 times bigger, and so on. That's the energy levels. The gaps between the energy levels keep getting bigger as you go up and up because of the n squared here. That's one of the characteristic features of the particle in a box model. Here's the energy level gaps for a particle in a box. It's h squared over 8ml squared times 2 times the quantum number n plus 1, which means that for the first few, for example, the gap between n equals 1 and n equals 2, the size of the gap is 3 times E0. And for n equals 2 to n equals 3, the size of the gap is 5 times E0, then 7 times E0, and so on. It's a pretty easy progression to see. All right, now, we're going to parameterize this model with properties of the actual molecules. So the properties we're going to use are the length of one bond. That's going to be an adjustable parameter. We're going to use solver by the end of this. That's a parameter that's going into our model, and it's going to be used as a fitting parameter in something like solver. Then there's a quantity L external. And what we're saying is that the total length of the effective box for our PIB model is the length of one bond times the number of bonds that are involved. That will change from molecule to molecule, right? Bigger molecule, bigger B, smaller molecule, smaller B, plus some extra little, I mean, maybe the electron can move a little bit beyond strictly the number of bonds available, so we add a little, well, it's really kind of a fudge factor. It gives us an extra parameter to adjust. That will help, has to help, right? So we add that little L external, or extra, I guess we'll call it. to that. All right, so then our delta E value becomes this. I've just replaced L squared with this expression. And then we say, all right, the number of bonds in the molecule is the same thing as the number of pairs of electrons, right? Plus the number of pairs, plus the lone pair. And so we can rewrite that B as a function of how many pairs of electrons there are in each of the molecules. I think it was 10, 12, and 14, right? And then we can rewrite our expression for the energy gap in terms of the number of pairs of electrons in the molecule, and that's a little bit more convenient. And then we can use the energy gap to predict the wavelength at which the absorption maximum will occur. And so that's just lambda, hc over lambda is equal to delta E, so lambda is hc over delta E sub n, and doing the algebra, that's what that is. And then we can start plugging in values and making predictions, subject, of course, to the values of the length of the bond and the extra little bit of length. And so we're going to adjust those two parameters. P is known, right? We know how many electrons we have. Everything else is known, fundamental constants here, number of electrons again. And so we just have those two parameters to adjust, and we're going to do that given the data that we have. So the length of the bond is about 0.139 nanometers, or that's the value that we will begin with at least. All right, so that's the first part of the lab. We're going to try to fit the absorption peaks, basically. That's the only piece of data we're going to take, 3 values, 3 different absorption peaks, 3 different values. The second half is to try to predict what's called the Einstein B coefficient from the PIB model and then fit that to the actual data that we get. So in this case, we're going to do some curve fitting. We have to say what, not just where the peak is, but what the whole shape of the absorption peak looks like. We're going to assume that only this first peak here is due to a single transition. These other peaks are due to other transitions, right? We don't want to include those. They don't count. We just want the peak due to one transition, because that's all our model accounts for. And then for that, we're going to calculate, well, we're going to calculate the area under that peak, and that turns out to be related to the value of this thing called the Einstein B coefficient. So let's talk about the Einstein B coefficient. Let's talk about transition dipoles. Let's talk about what makes an absorption band or an absorption transition either a strong or a weak one in general. In earlier classes, I don't know how much this has been talked about in your earlier classes. It's usually not talked about as much, and so let's spend a little bit of time talking about that. First of all, if you shine light on an absorber like a molecule, you can show that the rate at which transitions occur between the initial state, which we'll call 1 here, 1, and the final state, which we'll call 2, is proportional to something called the transition dipole moment. And here's the definition of the transition dipole moment. 1, again, is initial. 2 is the final state, the upper state here. For an absorption, right, 2 is the upper state. For an emission, for fluorescence, for example, 2 would be the lower energy state, because then you're emitting light rather than absorbing it. But this is absorption. So it's the final state, a dipole moment operator, and the initial state on the outside. We're taking the inner product between 2 states of the system and this dipole moment operator. I won't derive where this comes from. It comes from first order perturbation theory. Not terribly complicated, but beyond the level of this discussion at least. So let's do this calculation, or kind of do this calculation at least, for the particle in a box model. That's one thing that we're going to do. Calculate this quantity from the model and then relate that to the Einstein B coefficient, as it turns out. The second thing we're going to do is relate this quantity, or something close to it, to an experimentally measurable quantity. And that is going to be the integral, where is it down here? Let me go down there. The integral there, no, not there, under the curve for our absorption spectrum. So there it is, yeah. And we obviously we have to do some work to get down to there. But it's this integral over the absorption curve that's going to be the experimentally measurable quantity that we're going to relate to this Einstein B coefficient. And so we'll be able to calculate B both from the theory and from the experiment and compare the two, see how close we get. Okay, so first of all, here's the expression from the model, from the particle in a box. We're going to put in particle in a box wave function states for both the initial and the final state. Now, I don't choose n equals 1 and n equals 2 here. I choose n as some higher level because, after all, if we use our particle in a box model, some of the electrons are filling up states, and only the transition from the LUMO to from the HOMO to the LUMO is the one we worry about. So we're going from n to n plus 1. We're not going from 1 to 2, right? And what that n is depends on how many electrons the molecule has. All right, so then there's some math to do, some calculus. The particle in a box wave functions, this is the one for n plus 1. This is the one for n, right? Sine n pi x over L is a particle in a box wave function. This is 1. This is 2. And that's our dipole moment operator. The dipole moment operator is the charge on an electron times the x operator, the position operator itself. And so that boils down then to doing this integral. There's a thing from calculus that's useful. There it is. And if you boil things down, let's see, for some reason I jumped out anyway. We can't, I think one of the problems that it asks you to do is to derive what this transition dipole moment expression is given this integral. And so the reason I don't put it there is because you're supposed to do it. All right, that's getting the transition dipole moment, but now we have to talk about what this Einstein B coefficient is. And that Einstein B coefficient comes from a treatment of absorption of photons that's basically a kinetic model. This is basically the B coefficient is a kinetic rate constant. B here is analogous to a rate constant K in a chemical reaction. Rho here is analogous to the concentration of photons in a chemical reaction. And N here is analogous to the concentration of ground states for our molecules. So here's our molecule. It's in its ground state to start with, but it's going to make a transition up to the excited state. And so the rate of change of transitions, of absorption events, is going to be the rate of production of the upper excited state. And we're saying in our kinetic model here that that's a rate constant times the concentration of the two things that are involved, right? This is a reactant. The photons are a reactant. And so if we think of this as these two things as concentrations, this looks like a second-order rate constant expression. And that's essentially the idea. There are a lot of differences. The units are different and stuff. There are some subtleties involved when there's photons involved rather than ordinary chemical reactants, but the idea is essentially the same. So this B is essentially a rate constant, and we can calculate it from quantum mechanics, and that's what we're going to do. And let's see, what else do I want to say? Yeah, here's where I'm saying everything I just said up above, that there's an analogy between the kinetic model and this photon model. And if you do all the results, then what you get is that the Einstein B coefficient is equal to a cluster of constants, fundamental constants, so there's no inaccuracy or error here, times the transition dipole moment that we can calculate from the PIB squared. And so that closes everything in for one half of what we're trying to do, right? From the PIB model, once we get the expression from PIB for the transition dipole moment, we can use this to get an expression for the Einstein B coefficient. It is also possible to show, from a completely different point of view, that the Einstein B coefficient is related to the integral, well, some fundamental constants again, times the integral of something called the absorption cross-section, or extinction cross-section, as a function of frequency, divided by frequency. So you integrate basically the absorption band versus frequency, not versus wavelength, but versus frequency. We can always do that. Take this thing called the extinction cross-section, divide it by, which is basically this peak, divide it by the frequency itself, and this doesn't change very much. These absorption bands are pretty narrow compared to the whole range of frequencies. So this is basically a constant in this integral, and we'll make that approximation later, in fact. Then you get something that's very closely related to the B coefficient. This part of it is useful to look at, but it's basically explaining what the relationship is between this extinction cross-section, which is not usual for chemists, and the extinction coefficient. Where is it here? There it is. The extinction coefficient epsilon here in units of molar to the -1, centimeters to the -1. That's the thing that chemists normally use. And you can see they're very closely related to each other. It's just some basic constants, Avogadro's number being one of them, that relates the two of them. So when we're talking about the extinction cross-section, we're basically talking about the extinction coefficient. If you plug all that in, here we are back to the point that I came down to earlier, then this is the other fundamental relationship that you need for this part of the problem. There's some constants out in front. This quantity is the index of refraction of methanol, about 1.33, speed of light, Planck's constant, Avogadro's number, and then this integral over the absorption band. And then you can get, from our spectra, you can get the Einstein B coefficient. So you can get it now from the model and from the experiment. All right, and that's the essence of it. That's what we're going to do this week. A couple more notes. First of all, I say here to be very careful with units on this. Make sure. The problem with this calculation is that it mixes different types of units, different systems of units, all within one calculation, and that can give you, of course, units errors are always huge and disastrous. So be very careful that you're keeping all the units consistent throughout your calculation. When I was going through this myself, it took me hours to figure out how to keep the units straight. I've tried to make that a little simpler in the write-ups as they are now. I've modified the write-ups a little bit to help with that. And that's partly why I went through all these details up here, in fact. But it's still, the units in this problem are non-trivial. And so here are the normal units. This is the output of the spectrometer. That's what will actually come out, the number that will actually come out versus wavelength. When you take your spectrum, you'll record the spectrum onto a computer, onto a jump drive eventually, and eventually put it into a Excel spreadsheet. And the number that you're going to get, the numbers you're going to get are going to be wavelength and then an absorbance unit, A, as a function of wavelength. You're going to have two columns, one for wavelength, one for absorbance. And that's the extinction coefficient times the concentration of your dye, whatever it is, times the length of the cuvette that you use to do the experiment. That's 1 centimeter for our case. Extinction coefficients in molar to the -1, centimeters to the -1, and the concentration will be in molar. I think I mentioned this earlier, not today, but in an earlier class, that Amy and I made up these solutions a year ago. They're still good. We still have tons of it left. And so you don't have to make those up yourself, but you do have to dilute them. They're about 20 times too strong. If you put them in straight, first of all, you'd use a lot more of the stock solution than you need to use, but also you'll blast out the spectrophotometer. The beam of light going through the cuvette will actually get stopped. It'll only get about a tenth of the way through before there's no more light, and the detector won't see anything, and then you get really inaccurate results. So you got to dilute down enough so the beam can get through. And that means about a 20x dilution. You measure that very carefully because you're going to need to know that concentration in order to do the rest of the calculations. Here are the actual stock solutions as Amy and I made them up a year ago, and so they're in the notes and you can look them up. To do the integral that you need in order to get the Einstein B coefficient, you might be tempted. There is a version of this integral that can be done with using wavelength instead of using frequency. Basically, you just change the variable of integration here. It's a change of variables, standard calculus trick. So you can do it as a function of wavelength if you want, but I think it works better. I think it's probably more accurate to use frequency, and that means that when you're setting up your Excel sheet, the raw data is going to be as a function of frequency. You're going to have a column for frequency and then a column for absorption. It's better to make a column for, you're going to have a column for wavelength and then a column for absorption. It's better to make a column for frequency too, so that you can plot absorption versus frequency rather than absorption versus wavelength. Here's the relationship, of course. Then also, in order to do this integral, you can do it numerically, but you have to worry about the fact that you've got more than one transition going on at once, right? The peak that you're after isn't clean. It's got another peak, the tail of another peak coming in underneath it and contaminating it. So you've got to do some curve fitting in order to basically separate the peak that really counts, the peak for the transition we're modeling, from a peak from other transitions. And so there's any number of ways of doing this, and if you choose a good way, that's fine. We don't want to, if you want to be creative about that, we're all in favor of that, so we don't want to tell you what to do. But one way to do it is to use Solver on the Excel spreadsheet. There's another program called Davis, which I think Amy will tell you about. And I haven't used Davis very much, a little bit. Amy's used it a lot more, so she can tell you more about it. If you use Solver, though, here's what I did. You have your data, so let me kind of draw a picture here. Actually, let me, let's see if I can, maybe it's worth it. Just a second. Let me create a new file here. A blank file. So I can share it with, come on, there we go. With this, so now, there we go. Now I have some blank space. So you're going to have, on your Excel sheet, you're going to have a column for wavelength, you're going to have a column for absorption, all the way down, lots of numbers, hundreds of numbers. You can make a column for frequency now, right? That's what I'm suggesting. And then you should make a column for a fit. And I'm suggesting that the fit should be a Gaussian. You can use a fit that's a single Gaussian like this, and it has 3 parameters. The strength of the Gaussian, or basically the height of the peak. So a Gaussian peak is a bell curve, and that A is basically giving you the height of the peak. And then the center of the peak, so the mu there is the middle, is the position in frequency now, right? This is on the frequency axis, so that would be mu, where the peak center is. And then the width of the distribution, or the width of the peak, the standard deviation for the peak, is sigma. And so you've got 3 different parameters. That's an awful lot. It works better if you don't have so many. And so when I did this, you can pretty much tell what this A is, right? And you can kind of almost tell, you can tell to within just a little bit what this center is too, because your real peak, your real data, the center is going to be a little bit disturbed or distorted by the presence of these side peaks, but not very much. The true center of the true peak underneath is going to be very close to the one that's, you know, showing up in your data directly. So I took one Gaussian, so this red dot, this red dotted curve here, as my fit, and I just didn't even try to fit this other curve. And then I put this into solver, and I used that to solve for the fit. And then let's see if I don't think I have any pictures here of it. Maybe I can show that during the session on Monday. And then you can do the integral of a Gaussian analytically. You can do it on paper. Here it is down here. So you can show, once you've got the fit parameters for the peak, you don't have to do any numerical integration or anything like that. And that worked pretty well when I went through it. Let's see, is there anything else I need to say? Solver, peak centers, Gaussians, this approximation, which says that you choose the frequency that you put into your integral to be a constant, effectively a constant, because the width is narrow compared to the full width of nu. And then you can factor it outside the integral, and then yes, the integral that you want is just an integral over a Gaussian, and that's an easy integral to do. All right, well, I think that's it. I can't think of anything else to say at the moment. So we'll talk again on Monday, and you can ask questions if you have any. Thanks.